They laughed when they first saw it. Too heavy, too blunt, a machine that would never dance like the thin, wiry fighters that owned the early Pacific skies. The pilots across the water called it lumbering before it ever left the ground. Then, a 2,000 horsepower Heart, an engine in the roughly 2,000 HP class, model indefinido, began to scream, and the sky rewrote its rules. From the foundry to the flight deck, that is where the story lives. Picture a cavernous plant at dawn, steel ribs glowing orange under cranes, sparks flying as a grinder kisses a crankcase. The smell of oil and hot metal hangs low, a steady percussion of hammers and presses. Men and women in dark coveralls move like a single organism, measuring, tightening, listening. In the center, behind thick glass, a test cell trembles and the exhaust stacks hum. The engine inside is a promise and a threat at once. Promise of raw, sustained power. Threat in the way it will demand everything from metallurgy, cooling, and craftsmanship to reach it without tearing itself apart. The Pacific Theater at the start had a lesson that stung. Light and nimble fighters could glide circles around heavier, better-armed designs. Japan's Navy learned to exploit that advantage. Planes designed for agility, with minimal armor and long range, turned dogfights into contests of turning radius and nerve. Allied pilots watched as enemy fighters used their weight to vanish from firing solutions, as those thin machines bled less power in a tight turn and came home more often than the heavier types. It was easier in that first period to name the enemy's strengths than to see what might stop them. So the question became not whether one could build a plane that could turn as tightly as a zero, but whether in a different calculus of combat, turning radius mattered more than power, speed, and survivability. Could brute force, measured and refined as engineering, change the terms of the fight? Could a heavier fighter, fitted with a remarkably powerful and reliable radio engine, climb faster, dive harder, absorb damage, and still return its pilot to a carrier deck? The answer, when it came, was not a single discovery, but 1,000 small refusals to give up. The fight began long before the aircrew stepped into the cockpit. It began in test cells that shook like a held breath. Inside the test cell, something had to give. It wasn't cinematic glory, so much as grinding endurance, repeated runs to full power, sudden detonation that punched through a cylinder head, oil systems that choked at extreme RPM, bolts vaporizing in a chorus of failure. Engineers learned to read the engine like a patient reads a pulse, vibrations in places a human ear should not detect, temperatures climbing along a particular fin, a harmonic in the crank that meant impending fatigue. Every failure was a lesson encoded in ruptured metal.
To get a radial engine into the 2,000 horsepower class and keep it reliable in carrier operations required wrestling with several enemies at once: heat, vibration, combustion instability, propeller aerodynamics, and structural stress. Each of these is a subject with its own vocabulary, but they can be explained without losing the drama. Radial engines breathe through air that they themselves must coax across cooling fins. Get them to produce enormous power, and they produce enormous heat. In flight, airflow helps. In the test cell, the engine sits stationary, and the test engineers simulate that flow with giant fans and shrouds. But at high power, hotspots appear, thin ridges of metal that do not shed heat evenly. Cylinder heads can overheat, valve seats can fail, and pre-ignition or detonation becomes the invisible hammer that pounds pistons and rods until they falter. Then there is harmonic vibration. An engine is a system of masses moving in rhythm. Raise the power, and those rhythms change. Crankshafts can develop flex at certain speeds. Rods can bend microscopically. And if those vibrations align with a structural resonance in the mounting or the propeller gearbox, the results are catastrophic. A bolt that sheared on a night test might not be simply a bad bolt. It might be the symptom of an overlooked frequency where metal refuses to stay calm. Propeller physics adds another layer. A propeller is an energy transducer. It must convert high RPM torque into thrust without letting its tips approach transonic speeds, where efficiency collapses and noise becomes the least of the problem. Matching a powerful engine to a propeller requires choices about blade count, diameter, pitch, and reduction gearing. Those choices affect climb rate, acceleration, and the way the aircraft behaves in sudden dives, critical in naval fighter combat, where diving to escape or to pursue can be decisive. All of this had to be tamed on a production line that had to churn thousands of engines, day and night, for a war with no off switch. Tolerances were not academic. A few thousandths of an inch on a bearing race could separate an engine that would survive a mission from one that would arrive back in pieces. Manufacturing had to learn to be gentle and brutal at once. Gentle where precision mattered, brutal where metallurgy demanded overhaul. At the heart of the plant was the engineering office and the test crew, the human backbone. The lead engineer here is indefinito by name, but no less real. A man or woman with grease under the nails, who kept a pencil stub behind the ear and built habit around the cadence of the cell. They logged every test on a ledger, penciled notes in margins, and slept with the hum of turbines still in their ears.
Around them were the machinists who ground crankshafts until the sparks made an answering pattern on the shop floor, and the metallurgists who argued late into the night about alloy blends that might resist a specific fatigue crack. Composite recollection. We learned to treat the metal like a living thing. Reads a recollection assembled from the voices of many who passed through such plants. Composite recollection indefinito. You could see where it would fail if you left a corner too sharp. You could feel when a bearing was just a hair off. The engine would tell you. The words are not poetic inside the shop. They are practical. But there is poetry in the attentiveness, in the way fatigue cracks were chased down with chemical etching and borescopic inspection, in the way a machinist would tap a journal and listen for the sound of integrity. One repeated problem was cylinder head durability. At high boost pressures, the extra pressure forced into the cylinders to make more power, temperatures in the heads spike. Early attempts at increased power saw a litany of burned valves and cracked heads. The metallurgists responded with altered alloy chemistries and revised heat treatment curves. Reconfigured spark timing and optimized fuel mixtures reduced peak cylinder pressures. Oil cooling systems were rerouted with supplementary scavenge pumps and larger oil coolers placed where airflow would be most effective, not simply where layout was easiest. Cooling baffling inside the cowling, the arched plates that direct airflow over fins, was reshaped after engineers used flow visualization, sheets smeared with anemometer dust, to find dead zones. Vibration problems led to a revolution in balancing. Counterweights were refined, rods shot-paned to induce compressive surface stress that resists crack initiation, and crankcases were modified to increase torsional stiffness. Engineers learned that changing the profile of the propeller, adding an extra blade, shortening diameter, adjusting tip shape, could shift a problematic harmonic away from the band where the engine wanted to sing. That in turn required gearbox changes and further cooling adjustments, a cascade of modifications where one fix begot another challenge. Then came the test cell explosions that read like wake-up calls. Not large blasts that vitalized a war movie, but the more insidious failures. A piston that melted enough to fuse to the cylinder wall, causing the crank to seize. A valve that vaporized. A stud that let go and allowed oil to spray like mechanical confetti. Each failure was expensive in steel and in morale, but each failure also taught something no textbook could: how the real machine, with all its tolerances, responded under the stress of maximum output. Those long nights birthed innovations. A rethought oil circulation pattern meant consistent film thickness at bearings. Valve seats were produced in layers, with nickel inserts that resisted the hottest combustion gases.
Cylinder liners received coatings that reduced heat transfer spikes and made seizure less likely in an extreme scenario. The test cell engineers learned to run the engine through its harmonics, to precondition parts by controlled vibration so that the first full power run would not surprise them with an unmasked weakness. Manufacturing scale brought its own drama. It is one thing to perfect a modification in a laboratory bench run. It is another to bake that change into thousands of units on an assembly line. Supply chains were stretched. Certain alloys were in short supply. Particular heat treatment furnaces were bottlenecks. Managers had to prioritize which parts received the newly developed alloy and which received a stopgap until production could catch up. Decisions were made under pressure, with the knowledge that every engine that came off the line would go to a living machine flown by a person. Beyond metallurgy and shop floor tactics lay the impossible calendar of naval aviation. Engines had to be ready not only to start and run at sea, but to recover after being hit, to respond to sudden throttle changes, and to tolerate the salt and spray of carrier operations. Corrosion control, though less glamorous than a cracked headless in a test cell, was essential.
Seals were improved, drainage paths ensured, and protective coatings applied where microscopic pitting could bloom into catastrophic corrosion over a few months. Ruggedness was not an accidental byproduct. It was designed in, bolted in, and inspected in a cadence meant to withstand the abrasive reality of combat service. All the while, pilots and deck crews watched from the margins. On carrier decks, planes are a choreography of sequence and urgency. An engine that refuses to turn over can kill a strike. An engine that heats too quickly can delay launches and expose the deck to enemy action. The test sail's lessons would be judged at a different speed on the pitching wood of a carrier deck, under the spray and the smell of aviation gasoline and sea salt. So some experiments were meant less for the lab than for the deck, black box trials where modifications were flown and observed in the most unforgiving conditions. The narrative of the heavy Hellcat, an aircraft heavier than the nimble Zero, yet built around a powerful radial engine, is less about brute force and more about calibration. It's about a deliberate trade: accept more weight for armor and fuel, then use greater power to regain the mobility that weight sacrifices, while buying protection and the ability to sustain damage. That tactical idea is only plausible if the engine powering it can produce reliable, repeatable thrust at the levels demanded. Thus, the entire industrial drama funneled into that requirement.
The workshops developed a lexicon to match their new realities. Rev life, how long an engine could spin at a high manifold pressure before showing degradation. Sustain, a measure of how an engine handled repeated bursts to full throttle without losing integrity. Turnback, the ability to return home after taking ballistic damage. These were not simply performance metrics, they were survival odds. And in war, survival is a metric not easily quantified in graphs. Human stories threaded through the steel. There was the flight test engineer who refused to let a pilot launch until the vibration trace came back clean, and the pilot who insisted on feeling the plane himself because no meter could convey what his hands could. There were the machinists who stayed behind to overhaul an engine found wanting, and the metalworkers who retooled dies at the cost of endless overtime. There was a quiet, often forgotten class of workers, the inspectors. They stood with gauges and light bulbs over each engine part, turning a component until the light caught and a hairline crack revealed itself. That slow, patient work saved lives. By the time a unit finished the cycle from failure to fix, a pattern emerged. The engines that succeeded were not the ones that were the most complex or the most powerful on paper. They were the ones whose creators had learned to make power predictable. Reliability under fluctuating load and in the corrosive, jarring conditions of carrier life was the real achievement. A test cell could produce a spectacular run, a minute at redline that made heads turn, but what carriers needed was the engine that could do that day after day and still bring the pilot back. One technical payoff from months in the cell and the shop was the relationship between power and control. With greater horsepower came better climb rates and improved acceleration out of a turn. That extra shove let a heavier fighter dictate the terms of an engagement, to climb through an opponent's altitude band, to dive and convert that potential energy into speed, or to accelerate past an enemy's firing envelope. But raw power is dangerous unless tempered by control systems and aerodynamic design. Propeller pitch and reduction gearing mattered because they determined how that power translated into thrust at different speeds. The right prop could create a plane that felt agile, even if its empty weight and armor biased it toward mass. The wrong prop could make the plane feel lethargic and waste the engine's advantage. These adjustments had to be tried not only on stands, but at sea. Early sea trials were tense, ritualistic. Crews rode launches at dawn, the catwalk alive with blue overalls and slats of sun reflecting off canopies. Engines started in a chorus, magnetos clicking, starters whining, propellers surfacing sunlight into a blur.
Pilots felt the throttle response and called back to test crews. Engineers monitored temperatures and vibration from the deck, sending radios filled with numbers that meant life or failure. On one test sortie, an engine might scream up to full power and hold it steadily through a climb and a high-speed run. On another, an inexplicable vibration could send mechanics back to the shop with a handful of suspect parts and the knowledge that, until fixed, the whole line's deliveries were under threat. The psychological effect of this industrial confidence cannot be overstated. In the early months, Allied airmen feared going head-to-head with the lithe fighters that outsaw their numbers. But as engines began to behave predictably, as carriers received squadrons whose planes returned from missions with patched but whole structures, tactics began to change. Pilots could climb on command. They could engage in fuel-burning maneuvers, knowing their engines wouldn't burst into flame. The conversation shifted from, "What can we survive?" to,
What can we do with the power we have? This is a crucial point in the arc of the story, the transformation from a theoretical engineering victory, an engine that can produce 2,000 HP in the lab, to an operational reality on the carrier deck. That transformation is neither trivial nor instantaneous. It requires a confluence of successful metallurgy, manufacturing discipline, tactical adaptation, pilot training, and logistical support. No single part does it alone. And yet, as the plant calendar filled and crates of engines rolled out, the other half of the equation came into view: pilots, their tactics, and the doctrine that would leverage the new hardware. A heavy fighter, even with a powerful engine, needs a pilot who understands how to use energy rather than simply match a turning dogfight stroke for stroke. A pilot's training had to adapt to emphasize climbs, diving attacks, and hit-and-run engagement profiles where speed and acceleration replaced tight turning. On the carriers, pilots sat in cockpits that smelled of oil and leather and adrenaline. They ran through checklists that hedged against the engine's occasional temper. They learned to feel the airplane as an extension of the engine's heartbeat, to sense the torque, to feel the buffet that warned of an approaching stall, to take advantage of a power band that allowed for sudden acceleration when the enemy expected none. Deck crews, too, learned new rituals for running an engine hard and bringing it back without overtaxing it. By the time a squadron left the deck with those engines installed, the accumulated work of thousands of hands had been tested. The balance of prop and power, the strengthened cylinder heads, the baffling that directed air exactly where it needed to go, and the seals that kept the ocean at bay. The result was not perfection, but a new kind of dependability.
The aircraft could take more punishment in return. That changed the calculus of combat. This is the point, here in the arc, where the narrative must hold its breath. The machines are ready in a way they never were weeks before. Pilots are taking off, the test engineers have signed their approvals, and the carriers are loading strikes with a different confidence. But the story is not yet complete. The moment where this industrial and engineering toil meets the thin, nimble fighters across the water, the dogfight that would illustrate how this 2,000 horsepower heart could blunt the myth of light invincibility, lies just beyond the horizon. We stop then at the edge of that horizon, engines humming, crews tensing, and the carrier's decks alive with the ritual of launch. The foundry sparks and the test cells hum have done their work. Now pilots carry those machines into the sky, where rules can change in a second and where the consequences of every choice are measured in lives and metal. The next chapters will follow the flights, the engagements, and the reckoning that comes when engineering meets combat. On the carrier deck, everything moved with a purpose that felt like choreography and prayer at once. Ropes were tightened, chalks set, cats inspected. Men whispered into throat mics. A corporal's gloved hand tapped a prop blade and let it sing for a heartbeat, feeling for balance. A pilot in a leather helmet slid into the cockpit and closed the canopy as if sealing himself inside a temple. The engine behind him, the same engine that had screamed in test cells and survived their worst experiments, now had to sing on command, under salt spray, wind, and the threat of enemy guns. If you want more deep dives into the machines that rewrote history, hit subscribe. Launch was ritual, a last checklist, the bowman signaling, the launch bar linking to the catapult. When the throttle moved forward, the aircraft became a living thing. The instrument panel lit up like a mechanical constellation, and the engine's voice swelled from a simmer to a roar that filled the pilot's bones. In those first seconds, the difference between a machine that would hold together and one that would not was not obvious to anyone but those who had sweated over journals and blueprints. The pilot felt torque twisting the airframe and had to counter with rudder. The engine answered with a clean, consistent surge. That answer was not merely horsepower on paper, it was a promise that under stress, metal and oil and air would behave as expected. At sea, the advantages engineered in the plant were translated into tactics on the deck and in the sky. The heavy fighter that had been dismissed ashore now offered a different set of choices. Where a lighter fighter sought the seam of the turn, the heavier, more powerful aircraft used energy, altitude, speed, and acceleration as its currency.
A pilot could climb rapidly above an opponent, convert that altitude into a plunging dive, and build a speed that made the enemy's guns useless, then pull away before the opponent could bring his turning advantage to bear. This approach, often called an energy fight, accepted that the heavier plane would not outturn the light fighter, but could outpace it when it mattered. To make that work required more than engine power. The airframe had to be forgiving under high G pulls. its control surfaces harmonized to work with high-speed airflow. Armament had to be heavy enough to bring down an opponent in a brief window of advantage. Ammunition loads, gun convergence, and firing harmonization were adjusted so that a single hard burst could be decisive. Pilot training shifted from pure dogfighting to energy management. Climb aggressively, dive fast, make the short firing pass, then climb away to reset and repeat. On carriers, the cycle of launch, fight, recovery meant that endurance and the ability to return with battle damage were as vital as the kill itself. The engine's ability to sustain repeated bursts, to restart after rough handling, and to run while spewing smoke and oil was a central piece of that operational puzzle. The engine itself had characteristics that mattered beyond raw horsepower. Supercharging, the forced induction system that kept the engine breathing at altitude, needed to be matched to the mission profile. A supercharger that delivered boost at medium altitudes could turn a climb rate from adequate to commanding. It could be the difference between reaching an altitude band to force an engagement or arriving too late. But supercharging also raised temperatures and cylinder pressures. Engineers balanced blower ratios and gear reduction against cooling capacity and structural limits. The resultant service had to be an engine that produced usable power across the flight envelope, not just a peak figure on a test chart. Propeller choice was another decisive lever. A propeller that pulled hard at low speeds gave pilots explosive takeoff acceleration and better initial climb. A propeller optimized for high-speed runs allowed more energy to be converted into bite on a diving approach. The final production propellers in the squadrons were choices born from countless flights and breaks, compromises between blade number, chord, and tip shape, combined with reduction gearing that kept the prop tips shy of compressibility issues at high speed. Pilots learned the sound of the prop, telling them when they could safely push and when to conserve. Then came the skies, stretches of blue where the metal met intent, and where the work of the plant was tested against human adversaries. The following two vignettes are representative composite accounts assembled from multiple reports and recollections to illustrate typical engagements rather than to document a specific dated battle.
Representative Composite Vignette 1. A climb, a shove, and a fleeting window. Dawn lay low on the horizon, bruising the ocean to gray. A flight of heavier fighters peeled off the carrier, their engines breathing hard, their pilots scanning through glare. Across the sky, a small group of lighter fighters drifted, waiting for a moment to pounce. The heavier planes did not turn to bait, they climbed. The leader pushed the throttle to redline, feeling the engine's reply as it shoved the nose upward. Instruments rose, manifold pressure climbed, tachometer needles found their mark, and the formation gained altitude with a confidence that had been engineered into the crank and cam. At altitude, the leader saw an opening. The lighter fighters were below and ahead, banked in a sweeping turn. The order came over the radio. A wingman counted off dives. They pushed over one at a time, a coordinated cascade, converting altitude into speed. In the dive, the heavy aircraft became a streak. Air streamed over control surfaces in a way that turned the plane into a razor of velocity. The enemy, built to win in close turning fights, could not close the geometry fast enough. The heavy fighters' guns hammered a short, accurate burst into a vulnerable wing or fuselage. The enemy faltered, and the heavier planes were gone, climbing back into altitude to fight another set. No single flight was decisive, but repeated use of that energy profile eroded the lighter fighters' freedom to pick their moments. Representative Composite Vignette 2. Damage, endurance, and the engine that would not die. In another sortie, a lone heavy fighter found itself isolated, jumped by multiple light fighters. Tracers stitched past the canopy. One found a cylinder head, another slit a coolant line, and shrapnel peppered the cowling. The pilot felt the plane shiver and the engine cough. He pushed the mixture, cut the throttle briefly to clear fouled plugs, then eased the power back on. The engine answered, imperfectly, but it answered. Smoke trailed, oil pressure dipped, and then steadied. The prop carried its blades, though bent and ringing. Where an earlier generation of engines might have surrendered, this one kept a beat. The pilot gunned the throttle, used a diving push to escape the immediate fight, and began the long, ragged trip home. Carrier deck crews readied crash crews as the aircraft came in, but the pilot, exhausted, bloody, resolved, held the engine at a careful power setting and coaxed the airplane onto the deck. It was a landing riddled with scar tissue and applause without celebration. The machine had brought a man home. Both vignettes show something critical. The engine's value was not just in offensive power, but in survivability and recovery.
The aircraft's ability to return after damage kept experienced pilots in the fight, preserved institutional knowledge, and sustained squadron effectiveness.
The industrial design that allowed for field repairs, interchangeable parts, and parts that could be replaced at sea meant that the moment of damage was not always the end of a machine's service. In numerous after-action accounts, mechanics and armorers are credited with patching engines and airframes so that a plane could fly another day. That repairability was a deliberate outcome of production decisions, standardization of parts, easy access to service points, and the use of alloys that could be worked in forward repair shops. It is important here to be precise about attribution. The improved outcomes in aerial combat were not the product of horsepower alone. Training, tactics, pilot experience, radar-directed fighter control, sheer numbers, logistical reach, and industrial output all combined to change the air war's balance. The engine was a force multiplier. It amplified doctrine and training into practical advantage, but it did not, in isolation, rewrite the map. As production ramped, the theater itself changed. Squadrons flew more sorties, maintained air cover for longer periods, and could sustain attrition without immediate collapse. The psychological effect on both sides was real. Pilots who once feared going head-to-head with lighter, more maneuverable fighters now knew they could choose their battles. Opposing aviators found the skies less hospitable. Opportunities to isolate and wear down heavy fighters vanished as enemy commanders adjusted to the new operational reality. Yet with every technological advance came a moral and human ledger. As aircraft did more work, as industrial capacity enabled sustained strikes deeper into enemy territory, the consequences multiplied. Air superiority facilitated not only interdiction of military targets, but also operations that affected civilian infrastructure and populations. Those outcomes, the burning of cities, the displacement of families, the ruination of lives, must be stated soberly. Technology makes possible certain strategies. People decide to employ them. The men and women who hammered steel and tuned superchargers did so with the belief they were defending their country and comrades. The wider ethical questions of wartime strategy and its civilian costs belong to a larger conversation and deserve the gravity of measured reflection. Back on the technical front, logistics and scale created their own art form. Shipping engines across the ocean and keeping spares located where they were needed required a global choreography. Crates of parts had to survive submarine lanes, deck cargo handling, and the pummeling of storm and salt. At forward repair bases, men learned to cannibalize parts to keep fighters flying. Manuals were condensed into survival guides. Crews improvised gaskets and seals from whatever material was at hand. The engine that had been perfected in a factory had to be maintainable by a team with limited equipment on an island airstrip or aboard a carrier. This requirement shaped design choices: easy-to-remove covers, accessible oil pumps, and modular accessory gearboxes that allowed for quick swaps. One often overlooked aspect was the feedback loop between the front and the factory. Field reports, disciplined crack measurements, wear patterns, and failure modes went back to the engineers, who then adjusted production processes. A broken stud found on a forward line could lead to a change in heat treatment on a particular batch of fasteners across an entire plant. That loop shortened the lifespan of errors and spread the knowledge gained under duress back into the production stream. Human capital, the inspectors who logged tiny failures and the flight crews who described untoward vibrations, became a resource as valuable as any lathe or furnace. Personal stories give texture to this industrial tapestry. There was a chief mechanic at a forward base who would not allow a plane to launch until he had personally inspected the magnetos, a woman in the engine shop who rewound starters by hand to keep planes alive, and a foreman who folded his ledger closed with a tired hand after recording another unit's successful voyage back. Composite recollection. You got used to living in small miracles, one recollection reads. A plane would come back half a wing, and you'd patch it and put her back in the air. You didn't feel like a god. You felt like a stubborn shoemaker, making shoes that could hold a man. Technicians also contributed tweaks that were not in manuals. Field modifications, extra baffling here, a home-brewed oil cooler there, sometimes became formal changes in the assembly line. The distinction between factory idea and field improvement blurred in the urgency of conflict. What mattered was what worked and what could be sustained in the environment where the engines met the most severe tests. The strategic shift in the theater was not immediate, nor was it total. The enemy adapted.
tactics evolved on both sides. Lighter fighters began altering their approaches, using new interception vectors, employing altitude tricks, and integrating with ship-based fire control to create layered defenses. But the heavy fighters' increasing presence and the assurance that a pilot could come home even after serious engagement altered command decisions. Tasking changed, escort patterns shifted. Commanders who once feared attrition from enemy fighters began planning offensive operations with different assumptions about acceptable risk. Manufacturing continued to drive the war in ways subtle and stark. The capacity to crank out thousands of rugged engines enabled attrition to be absorbed and replaced. Training pipelines filled with pilots who could expect to fly machines with a higher survival probability. That fed morale and encouraged risk-taking within doctrinal bounds.
Conversely, any strain on the supply chain, shortages of alloy, bottlenecks at a heat treatment furnace, interruptions in shipping could quickly ripple into vulnerability. Production was a strategic asset, and its preservation was a matter of national survival. As the calendar turned and carriers returned to home ports for refit, stories multiplied of planes that had come back with engines smoking and bodies bent, of pilots whose lives were extended by the dependability of the hardware. In hangars on quiet days, mechanics sat on crates and whispered about the machines with something like affection. The foundry had begun as an abstraction for many servicemen. For those who had labored over pistons and bearings, the engine was less a tool and more a companion that had been coaxed into trust through the skill of many hands. Those quiet moments in hangars, where oil-stained faces met metal in a kind of reverence, formed the emotional backbone of the end of this story. The roar that once announced a mission was, in peacetime, replaced by the hollow echo of a museum engine that still smelled faintly of oil. In museums and memorials, the machines sit on pedestals behind ropes, polished and silent, often stripped of the grime that made them function. Visitors may admire lines and curves without feeling the hot pulse that once made them terrifyingly alive. Veterans who come back to those machines sometimes place a hand on cooling metal and speak in low voices to an engine that had once been a companion in danger. We must not romanticize those hands and that metal. Many who built and flew these machines paid with health, life, and years of peace stolen by war. The factories operated on overtime, and the repeated stresses of grind and shock left marks both visible and invisible on workers and aviators. The technological triumph was inseparable from human cost. A responsible telling acknowledges that the same ingenuity that enabled greater effectiveness also enabled more destructive strategies. The story of engineering excellence thus sits beside a ledger of consequence. When the dust of war settled and historians began to parse causation, the role of the powerful radial engine was clear but contextual. It was an enabler of tactics that emphasized energy and endurance. It was a foundation upon which doctrine and logistics built operational advantage. But it was never the sole determinant. Pilots, tactics, radar, numbers, carrier tactics, crew training, and sheer industrial mass all interlocked. The engine was a critical node in a network of capabilities that together reshaped control of the skies. In the end, there is a peculiar irony to the narrative. What had been mocked as heavy proved, in context, to be a kind of survival-focused wisdom. Weight was traded for armor and fuel. Power was added to reclaim mobility. And through iterative, often frustrating work on test cells and assembly lines, a dependable machine emerged.
The mockery from the other side of the ocean, the taunt that a heavier plane could never match a lighter one, was not a simple error of judgment, but an expression of a different strategic choice. The heavy versus light debate is not about right or wrong in the abstract. It is about decisions matched to doctrine and industrial capability. And so the story closes where it began, with a heartbeat of metal and a chorus of hands that refuse to accept failure. The test cell hum and the foundry hammer have yielded to silence in many places, but the lessons remain. Reliability under stress, the courage to iterate, and the humility to let field experience teach the factory are engineering truths that outlive any conflict. In a corner of a museum, a radial engine sits polished and inert, its cylinders gleaming. A plaque will tell part of its history. It will not tell the names of the machinists who peered through magnifiers to find a hairline crack, nor the pilot who coaxed a dying machine home under fire. Those names exist in letters, in small notebooks, in the memories of the few who remain. If you listen closely to the recorded interviews, to the tattered logbooks, to the cadence of oral histories, you will hear two persistent notes. One is technical, the careful, often tedious arithmetic of metallurgy, airflow, and the way torque becomes thrust. The other is human, the stubborn devotion of people who made power predictable so that a pilot might return. The engine's roar was a language spoken by both groups, and in that shared language lives the complex truth of this story. Like any instrument of war, the heavy fighter and its powerful heart carried dual legacies. They changed the balance of forces. They made some tactics obsolete and others possible, and they protected some but exposed others. If the title suggests a reversal of expectation, mocked as heavy, then vindicated by power, the fuller truth is that engineering, industry, and human will combined to create an option where none seemed available before. That option altered decisions, and in the process shaped lives and destinies. The last image, then, is not of triumph but of quiet continuity. A veteran walks past the display case in a museum and pauses. His hand hovers for a moment over a prop hub, not touching, but feeling memory. In the distance, beyond glass and pedagogy, children gather in circles of noise and light, unaware of the sacrifices that enabled their afternoon. The engine rests, its work complete, its voice a memory that still teaches engineers, pilots, and citizens about the cost and consequence of making power reliable. If this story resonated with you, like, share, and subscribe for more accounts of the machines and the people whose work quietly shaped history.